Hi all and welcome back to Nunley Math. I'm your host Aaron Nunley. Thank you so much for joining us as we begin to look at how we can use what we've learned about systems of linear equations to begin to solve increasingly complex application problems. Now the intention is to introduce you to the basics of writing linear systems from word problems in this video, and then over the course of the next several videos to look specifically at um, very common systems applications that tend to fall into recognizable patterns, that problems that seem fairly difficult if you're not familiar with the pattern, but once you become familiar with the patterns, they become much simpler to do. So we'll deal with the most common types of systems applications, work problems, mixture problems, digit and coin problems over the course of the next several videos. But for today, it's just going to be some basic application problems, things that might seem slightly familiar to you if you've been watching the videos as we've come along, but certainly we're going to expand on those just a little bit here. So without further ado, let's get started. Here's a very common problem. I snagged this out of an old textbook off my shelf. It says a baseball team played 162 games. They won 44 games more than they lost. How many games did they lose? Now there are a couple different approaches we can use in solving a problem like this. One we learned earlier this year when we were talking about single variable equations, but we're going to set this up as a system this time. As with any application problem, it's important for us to begin by asking ourselves, what is it we are being asked to figure out? Because that's always our unknown, which makes it our variable. In this case, that's very easy to spot because you can see at the end of the problem there's this question: how many games did they lose? So our goal is to figure out how many games they lost. I'm going to assign that a variable. I like the letter L. L reminds me of losing. Please keep in mind that a lot of students prefer to always use X and Y. I tend to like to pick letters that help remind me of what I'm talking about. But certainly the variable you use is entirely up to you. It doesn't make any difference as long as you can keep it in mind. X and Y tends to be very helpful if you're going to have to graph your information at some point. So once we know what it is we're being asked to find out, we want to start looking for relationships. We talked in a earlier video, much earlier in the year, back when we were dealing with single variable word problems, about how to read word problems for meaning. In this case, when I read, I see a baseball team played 162 games. Now, at first glance, that may not seem like a relationship. It might seem simply as a statement of fact, or as we called it earlier in the year, a piece of information. But this actually does give us a relationship, particularly when we think about the variable L, losing, because the total number of games you play should be the sum of your wins and losses. Now this of course is assuming that there are no ties, but the problem doesn't make any mention of ties, so we're for now going to assume that there are no ties. So our wins combined with our losses should total 162 games. Since we don't have a number of wins given to us, we're going to go ahead and assign that a second variable. I'm going to call that W for the same reason as before. W reminds me of games won, just like L reminded me of games lost. And I can take this expression, wins plus losses equals 162, and I can write it algebraically as W plus L equals 162. Let's look at the second sentence. They won 44 games more than they lost. They, being the baseball team, win 44 games more than they lost. So however many they lost, the number of wins was 44 more than that. So I take my losses, add 44 to it, and it gives me my number of wins. You could also think of that backwards and say your wins take away 44 equals your losses, but this is a more literal translation of what's written. And of course, using W and L, I can write it this way. My wins equal my losses plus 44. I went ahead and switched the order here. It is more common to put the variable first. Also, if we were doing a literal translation, we would say the wins were equal to 45 or 44 more than. The word than indicates that we have to switch the order. In the case of addition, it doesn't matter a whole lot because addition is commutative, but I wanted to be consistent. So, we now have a system of linear equations. We've got this first equation written up here in red, w plus L equals 162. You've got a second equation written here in blue, w equals L plus 44. And I'm just going to bring those two down here. We have two options for how to solve this. We can either use the substitution method or the addition method. You'll remember the addition method is also often called linear combination or elimination, depending on which textbook you're working in. The name doesn't matter so much. Typically, we will use the substitution method if we have a variable that's by itself. For example, we have a w by itself over here. And we'll use the addition method if both equations are in standard form. You'll remember standard form has your first variable added to your second variable equaling some constant or some number. So in this case, we have one of each. Since we already have this variable by itself, I'm going to use the substitution method. If a variable is by itself, usually that's the easier way. Just to remind you, the substitution method says, if you have an equal sign, w equals L plus 44. What we're saying is that the thing on the left and the thing on the right have the same value, which means anywhere you see the value on the left, you can replace it with the value on the right. When we did this in our earlier video, we talked about how anytime somebody asks you for $1, you can replace it with 4 quarters because they have the same value. Anytime anybody asks you for 50 cents, you can give them 5 dimes because they have the same value. The same thing is true here. One of these can be substituted for the other at any point in time. So what I'm going to do is I'm going to take this L plus 44 and I'm going to substitute it into the first equation instead of the w. Since it has the same value, it's not going to change the truth of the equation. So notice I've taken that red equation, replaced the w with the L plus 44, and now I have a new equation. We like this new equation because this is a single variable equation, which is very easy for us to solve. I can use my commutative and associative properties to rearrange and then use my distributive property to combine my L's. I get 2L plus 44 equals 162. I use my property of equality to subtract 44 from both sides. That leaves me with 2L plus 0 equals 118. The plus 0 is unnecessary, so I go ahead and I don't write it down. That's the identity property. I have 2L equals 118. To get rid of the times 2, I divide both sides by 2 using the property of equality, and that leaves me with L equals 59. Now, once I know that L equals 59, I have to take that and answer the question that was asked. How many games did they lose? The answer to the question is, they lost 49 games. Now actually this is a typo, this should be 59, so I do need to go back and correct that in my slide show. So I'll make sure I take care of that here. They lost 59 games. Now I could go back and find how many they win as well because I know the wins are equal to the losses plus 44, but the question didn't ask me that information, so I'm not going to bother giving it. I can, if I wanted to, also check to see if my answer is correct by using the wins and losses. 44 wins and 44 more than my 59 losses means 103 wins. 103 wins plus the 59 losses gives me the 162 games, which is what we said should happen in the first place. Does that make sense? This process over here, defining variables, looking for relationships and using those to write equations, Solving the equations or solving the system and then answering the question is our strategy for all of these. The difficult part is step 1 and step 2. You should not at this point be having a whole lot of trouble with solving the system. If you're having trouble with how to solve the system using substitution or addition, this is not the video you need to be watching. You need to go back and watch the video on solving those. Our focus is going to be up here. I will tell you that a lot of students like to try and rush through this process. They don't take their time when defining variables. They're not careful when writing the equations. And because they take shortcuts here, they end up struggling down here. This is where the work takes place. This is where you need to take your time and be careful. Now, I do not require my students to write these out in words and then write them out in words over here. I do let my students jump straight from defining the variable to writing the equations. But this thought process is how we arrive at that, so you want to make sure you're spending an appropriate amount of time learning to do that. Let's try another one. An automobile dealer sold 180 vans and trucks at a sale. He sold 40 more vans than trucks. How many of each did he sell? Using our process, we're going to define our variables. The question says, how many of each did he sell? This word each indicates for me that I'm going to have more than one unknown, which means I need more than one variable. We know he's selling vans and trucks, so I'm going to define my variables as V for number of vans sold and T for number of trucks sold. Notice I don't mind to abbreviate the word number using a symbol, but I am being very careful not to just say vans or trucks, but it's the number of trucks that were sold. You might run into some problems with vans that are sold as well as vans that are bought, or vans that are sold on Tuesday versus Thursday, so you want to make sure you define this very specifically. The more specific you define your variables, the easier it's going to be when you go to the second step. We're looking for relationships. The problem tells us the dealer sold 180 trucks and vans. Here again, just like in the last problem, we're given a total of 180. Well, that's the number of trucks and vans combined, which gives us this equation. The second sentence tells us he sells 40 more vans than trucks. 40 more vans than trucks. This also can create an algebraic equation for us, but we have to be very careful here. This expression, 40 more vans than trucks, causes a lot of students problems because it's very difficult to tell what we're adding the 40 to. Because I see 40 more vans, it looks like 40 plus V. But this says he sold more vans than trucks. That means the vans has to be the bigger number. Because of that, the number of vans is equal to the trucks and 40 more, or V equals T plus 40. Once again, we have our system. As I look at these two equations in my system, what I notice is that this V is once again by itself right here. Because this V is already by itself, it is probable that substitution is going to be the preferable method here. So I'm going to take this T plus 40, substitute it in for the V, and create this new equation. Notice it's just the red equation with the V taken out and being replaced by the T plus 40. This is just a single variable equation. Just like before, the solving here really shouldn't be overly complex for you. You end up with T being equal to 70. Now in this case, you are asked to find the number of vans and trucks. So once you know the number of trucks, you must go back and find the number of vans, which is pretty easy. We're just going to take this 70 and plug it into either one of these equations. It doesn't really matter, but this second one looks like it might be a little easier. So I take the second equation, plug the 70 in, and I end up with 110 vans. The answer to the question then is the dealer sold 70 trucks and 110 vans. If you wanted to check, the 70 trucks plus the 110 vans is 180 total, as we were told in the problem, and the 110 vans is 40 more than the 70 trucks, which we were also told in the problem. Does that make sense? If you define your variables well, and if you look carefully at each sentence, more than likely you're going to be able to generate your equations without a whole lot of trouble, but you've got to go slow. Shirley is 21 years older than Laura. In 6 years, Shirley will be twice as old as Laura. How old are they now? Here's another typo. We'll fix that real quick. There's your question mark. Let S equal Shirley's age and L equal Laura's age. Now, you'll notice that we are supposed to define our variables, but the question has already done that for us. Now, I've said before that you can pick any variable you want. If the question assigns a variable for you, you need to use whatever variables they give you. Since they've defined the variables, we can start looking for relationships. Shirley is 21 years older than Laura. I would suggest pausing the video and trying to write that equation on your own. Hopefully, you came up with S equals L plus 21. You also could have done that as L equals S minus 21, but this is a more literal translation. This second sentence is a little bit more difficult, and we do need to talk about this really quickly because these kinds of problems tend to create difficulty for students. It says in 6 years, Shirley will be twice as old as Laura. We have to keep in mind that in 6 years, both Shirley and Laura will be older. That means that Shirley's age in 6 years is S plus 6. Laura's age in 6 years is going to be L plus 6. If we keep that in mind, this second sentence creates an equation for us very nicely. I'd recommend that you pause this and try it on your own before watching me explain it. Hopefully you've done that. Shirley in 6 years, notice that's your S plus 6 right there, is going to be double Laura in 6 years. There's your equation. S plus 6, Shirley in 6 years, will be double, that's 2 times, Laura in 6 years. Now, this is a messy little equation. I probably wouldn't leave it like this. I would probably go ahead and distribute my 2 using the distributive property, and then use my property of equality to move the 6 over. It's going to give you something that's a little nicer to work with. You could technically leave it this way and work with it within your system, but I think you're going to find that to be unpleasant. Step 3. I have my 2 equations. I can either use substitution or addition. Notice that in both these equations, the S is by itself. If you ever have a variable by itself, that is usually an indication that substitution is going to be easier. So I'm going to take that 2L plus 6 and plug it in for S in the first equation to create this new equation. Notice all I've done is take that first equation, replace the S with a 2L plus 6 to get this new one. And here again, we'll subtract the L with the property of equality, subtract the 6 with the property of equality, and we get L equals 15. In this case, the question says how old are they? So they not only want Laura's age, they also want Shirley's age. You now know that Laura is 15. I can take either of these 2 equations to find Shirley's age. I'm going to take the first one, not just because it looks a little bit easier, but I remember that I did some computation and rearranging on that second equation, and if I plug it into that one, there's a chance that I may have a computation error that gives me some grief. So I'm just going to use the first equation, plug in the 15 that I know, and it gives me the S that I don't know. Always make sure you answer the question. Laura is 15 years old and Shirley is 36. If you felt like double checking that, Laura, who's 15, plus 21 years would, in fact, equal 36. Shirley is 21 years older than Laura. And in 6 years, Laura will be 21, and Shirley will be 42. So Shirley will be twice as old as Laura, which is what the second sentence stated. It's always a good idea to go back and just double check that you haven't done anything silly or foolish. Make sure that your final answers make sense. Got one more of these for you. 4 pencils and 2 pens cost 74 cents. 6 pencils and 5 pens cost $1.53. Find the cost of a pencil and a pen. This one's actually one of the easier types in my opinion because you've got two of the exact same story. In both cases, we're trying to find the cost of a pencil and a pen. Notice that this time I just decided to do something different just to mix it up. I used capital P for a pencil, lowercase p for a pen. There's no problem with that other than the fact that if you're not careful it can get a little bit confusing. I just thought I'd do it to be obstinate today, so enjoy. Take just a second and see if you can write these two expressions on your own. 4 pencils and 2 pens are 74 cents. I wrote it this way. 4 pencils and 2 pens are 74 cents. Can you do the second one? 6 pencils and 5 pens cost $1.53. Here's what I got. Notice this time that both our equations are in standard form. Because they're both in standard form, I'm going to use the addition method. I could rearrange these so that one of these variables is by itself and use substitution, but probably that's going to be more work. Remember, the goal with the addition method is to add these two equations together to create a third equation where one of the variables is missing or becomes a 0. Notice that 4p plus 6p does not give me a 0. That would give me a 10p. And notice that 2p and 5p give me a 7 lowercase p. This is a problem for me because neither of the variables disappeared. So what I'm going to do is go back and erase all the ink on the slide. And we're going to go ahead and try and change these equations using the property of equality so that either these two terms or these two terms are opposites of one another. Let me erase that again. I'm going to multiply through my equation by -5, the first equation by -5, and the second equation by a +2. If I were to do that, the first equation becomes -5 times 4p is -20p, -5 times 2p is -10p, and -5 times 74 cents is $3.70, and then it's negative. The second equation, 2 times 6p becomes 12p, 2 times 5p becomes 10p, 2 times $1.53 becomes 306. I like this much better because when I add this together, -20p plus 12p becomes -8p. -10 and +10 go away. -370 and 306 become -64 cents. I intentionally multiplied by numbers over here to create terms here that were opposites, 10 and -10, ensuring that I would get them to disappear, because now I have a single variable equation. How to get rid of times -p? Divide both sides, or -8p, divide both sides by -8, giving me p equals 8 cents. Again, the question says find the cost of a pencil and a pen, which means they not only want me to find the cost of the pencil, but I have to take this, plug it back into either one of these equations to find the cost of a pen. I happen to choose the first one because it had smaller numbers. I plug in 8 cents for the pencil because that's what the capital P stood for. 4 pencils then is 4 times 8 cents, or 32 cents. I subtract that 32 cents from both sides. What's left over is 2 pens for a cost of 42 cents. Divide both sides by 2, and I find that a pen is 21 cents. The answer to the question then is pencils cost 8 cents and pens cost 21 cents. Now, whenever I ask this question in class, I always end up with a student who has this question. Doesn't it say find the cost of a pencil and a pen? Yes, it does. You can possibly interpret this as asking what would the cost of one pencil and one pen be? If the pens are 21 cents and the pencils are 8 cents, you could make the argument that a pen and a pencil costs 29 cents. And you could have that as your final answer. Again, this is not a well-phrased question because we should be able to tell without having to think too hard about it which of these two answers it is. But one of those answers is the one you would want to give. If you are unsure, you would want to give both. As always, thank you so much for listening. Make sure you hit that like button. Make sure you subscribe so you don't miss any of the Algebra 1 we are covering. This next several slides, or next several lessons should be pretty interesting for you. It should answer some age-old problems, and really we're going to look at some classic problems that students have considered to be difficult for many, many years, but hopefully we can make those pretty easy and straightforward for you. As always, thank you for watching. Best of luck to all you guys. Take care. Bye-bye.